Exercise 116. Let's talk about the ring decrease. Remark: one disadvantage of p-adic plus is that the Frobenius automorphism does not preserve the kernel of theta. We have discussed this before. So there is no natural Frobenius automorphism. Of p-adic. Right. So to solve this problem, or to improve this situation or remedy this defect, we introduce another period ring decrease. So let's prepare for that. So we have discussed, I've constructed a ring map theta. Yeah, this is the famous theta. And then we extend this by invert P. To CK. With the kernel of theta either generated by C or, yeah, so here you could only use C. Because yeah, we're under our construction. So T is, it's okay, it is in p-adic, and so in p-adic plus, but we don't know it's in WR or not, which means C p-adic is the same as T p-adic, right? But this doesn't tell you C WR is the same as TWR. Let's recall one more time. C is omega plus P below the form. And this is inside WR. And this element in R is the one whose zero position is minus p. Remark 3, definition. Definition. The module increase 0 is defined to be the divided power envelope of WR with respect to the ideal kernel theta. In other words, it is a JK stable WR subalgebra in WR 1 over P. So the divided power envelope of WR with respect to ideal generated by XC is contained in WR invert P. Let's write it more precisely. So increase 0 is WR a to the power m factorial. So we're adding all those terms in the way of polynomial for every a in kernel theta. In other words, this is also the same as just WR C to the power n factorial for any n integer. Wait, so I'm now again feel curious. I remember I have a probably stupid argument that we have this K bar embedded into R. Yes, this is the residue field, and then this induces a map from WR to WK bar to WR. I would say still injective map. But then this contains CP, yeah. And then if you invert P, this contains QP. Yeah, and in particular contains all those factorials. Yeah, I think this this is why everything is contained WR1 over P. I guess this works. Good. Third remark. So we're going to define a crease. So before we define crease 0, now we define crease to be inverse limit of a crease 0 quotient by p powers. This is abstract p-adic completion of a crease 0. Remark 3.1. The description of a crease is complicated. And verifying even its most basic property requires a lot of work. So we just describe some without proof. So more techniques should be looked or should be checked in Fontaine's original paper. So let's say, firstly, let me put ABC. A crease 0 is naturally a ring. Things if you put c to the power n, m over m factorial, and then you will notice that under multiplication, this is again a divided power up to multiplication by some integer. Good, interesting. Secondly, this is actually it's a domain at flat azimuth. Thirdly, the natural map decreases 0 quotient p to the power n to a crease quotient by p to the power n is an isomorphism. So the phenomenon here is similar as p-adic completion, for example. P-adic completion for, yeah, this is just p-adic completion, so nothing surprising here. Let's see remark 4. It can be shown that there exists a unique, continuous, injective, and GK equivalent map, let's call it J, from a crease beta RAM plus. Search that. The following diagram commutes. So we just relate this increase with beta RAM plus. So how is this vertical map from increase 0 to increase? There a section? Or we put the wrong direction of arrow? Let me check. So we claim this is injective, so I guess we I'm sorry. This is just because this I'm sorry, so this is not the piece of the quotient. This is just the completion. It's like Z embeds into ZP. Right, this is not section, this is just the completion. And so this is embedding also, yeah. And here we have WR invert P. Again, because this is the kernel p-adic completion. So really we're carting out something. Right, we're carting out something from both sides. So this also should be embedding commute. So from the commutative diagram and the fact that J is injective, it implies that this makes Chris 0 as a subring of a Chris. Actually a subring of beta and plus even, right? So concretely, the image of a Chris in beta and plus is the subring of elements so Chris 0 equals W of R C to the power n factorial equals, for all integer n bigger equal than 0, alpha n to the power those alpha n tends to 0 p-adically and goes to infinity. Actually, think about it. Think about it, why it is not just the finite power series, because we picked the p-adic completion, so here we made a mistake. This is a Chris. What we do is we're talking about a Chris. Otherwise, it's just the finite. So, talking about the Chris, which is the inverse limit p power. That's why you are loving formal power series, but p-adically tends to p-adically the term goes to 0. So, in which the infinite sums are taken with respect to the discretely valued topology on beta and plus. increase is as remarked the ZP flat domain. And then the rim map theta from WR to OCK can be extended to increase 0. And therefore to increase. So draw a picture. Descending divided power. Consider increase. Completion. Still call this theta crease. The p-adic completion is still there, and because OCK is p-adic complete, this has not yet to do with this ZP flat domain. Let's do the exercise. Proposition. The action. So let's just mention this. I don't do this. This is very technical. So proposition. The JK action on increase is continuous for the p-adic topology. Decrease is complete for the p-adic topology. Now the JK action is continuous for this p-adic topology. Equivalently, for any integer n bigger or equal than 1, the JK action increase quotient by some p power has open uniformizer stabilizer, because this is a discrete topology on the quotient, and so it's open means any point has pre-image is open, so which means stabilizer is open. But GK action is continuous is something quite long to prove. So exercise first part. Proposition. The kernel of theta crease from A crease surjective to OCK is the divided power idea. In other words, if A is element of a crease such that theta crease acting on A is 0, then for any so if small is in the kernel, then for any integer positive a to the power m divided by m factorial is in a crease. So divided power ideal means any element of this ideal, its divided power is also there, right? So theta crease of this divided power is also there. So by this we mean we checked any element of the kernel, its divided power is there. That's what we have to check. Proof. It's just computation. Okay. So for this is small, you retain the form as we just described. So divided power increase 0. So this is a finite summing increase 0, right? We have e to the power m factorial equals so this is a to the power m, and a is this. So this would be product n a n c n times j n over n factorial the power j n factorial. And then I show that this is because we need divided power, so we are going to move this power out, c to the power njn, and so njn factorial, and then njn factorial, and then n factorial, jn factorial, and so this part comes out, right, comes out to be gamma n j n of c, and so this part falls into increase 0. And this is not very related with other things. This is just a computation. So better understand this, put this as a sub-exercise to really do the computation. Remark. By reducing modulo p, the image of theta crease we have a ring homomorphism. Let's call it theta crease bar, which is a crease, theta crease OCK modulo P. So let's second remark. The kernel of this theta crease bar comes from, could be generated by the kernel of theta crease, and P is again a divided power ideal. In other words, for any element, a kernel of theta crease bar, then and for any integer m positive, a to the power m divided by m factorial is again here in a crease, and theta crease bar kills it. Remark 3, if take an element in a crease, then A can be written not uniquely into the form summation an times cn n factorial with an wr and n goes to 0 p-adically. This is what we have described just now, right? Here, let's mention it's not unique. And now let's mention that for the element t, it could be written as minus 1 to the power n plus 1 0 minus 1 to the power n divided by n. This is in Bidoran plus. Notice that, or recall that this is in the kernel of theta, kernel of theta for WR to OCK. We have this element could be written as power of C. There is this element WR, right? And so you could write this differently. This would then become CB to the power n over n, and so this is C to the power n factorial, and minus 1 factorial over B, times B to the power n, and so this is minus 1 factorial B to the power n times gamma n of C. Right, so you retain it in the form of some divided power and with some coefficient, and notice that this coefficient goes to 0 p-adically. Basically, the valuation of this goes to infinity. The p-adic valuation of this goes to infinity. Exercise 2. Proposition t to the power p minus 1 is contained in p increase. So the conclusion is that t is here in increase. So t power is also increased, but we claim that t to the power p minus 1 is moreover the ideal generated by p inside p increase. We need to show that this epsilon minus 1 to the power p minus 1 is contained in p increase. Why? Because of the expression of t, right? So t to the power p minus 1 is summation of something. Just don't care about that. Something to the power p minus 1. Yeah, because this was already in increase, which means anyway, once you could prove there is a p in each term, then just move that p outside, and what is left there is still inside the crease. Do we have to worry about the denominator? And no, that's not a problem, not at all, because just forget this. You look at there, right? Yeah, really nothing to worry. So let's do the computation. Epsilon minus 1 equals epsilon minus 1, the first position, and that's it. Not, we don't care about the others. And then epsilon minus 1 to the power n, so the nth component of it, this is in R. Nth component of this would be by definition of addition. M goes to infinity. This is epsilon plus m minus 1 plus m, which is 1 raised to power p power m. And notice that the Pn is epsilon n, it's primitive. I would say, so don't worry about that, because when you take n factorial, you're always left with integer coefficient there. Those denominators, you don't have to worry about that, because that's always encoded in the n factorial, okay? Epsilon n is a primitive pnth root of unity. If we put pi equals epsilon minus 1, or what I want to say that this is uniform. This is uniformizer for the p-adic. Wait for the, let me just put pi equals epsilon minus 1 at this moment. Then we have valuation of nth component. Is p times p to the power n to the 0th component. And we know what is the valuation of this. This is p or p minus 1. We have computed this before. So we have this. On the other hand, we have epsilon minus 1 to the power p minus 1 is pi to the power p minus 1. The valuation of pi to the power p minus 1 is because that is p over p minus 1, so this is p, and so it equals p valuation of this, because this is 1 by the construction of omega bar. So we have epsilon minus 1 to the power p minus 1 equals omega bar to the power p, where up to a unit, right? Use a unit for R. So this is in R. Now bracket epsilon minus 1 to the power p minus 1 is congruent to similarly to omega to the power p times u so you tilt because this is just epsilon minus 1 0. Wait, I'm not quite sure. This is multiplicative, it's okay. But the tertiary if the epsilon minus 1 is a tertiary if the epsilon minus. So, which means this is multiplicative, yes. But it's not additive in general, right? Is it in this case just as simple as just addition on the first component? Let me really check it. Not obviously the second position 0, right? but when you take the tetrameter left, so it gives a congruent modulo p. That's okay. A little confusing, so I have to show that this is contained in P ideal generated by p-adic. So I left as sub-exercise to check that this is the same congruent to firstly. Congruent to this. And so this is congruent, there's no problem. When you lift a unit, this is again a unit. Doesn't matter, this is a unit element. This will further congruent to, I mean modulo p element, right? Because from the tetrameter lift, and if you mod p, you go back. And it's the same as modulo p or not. U. And I claim this is congruent to C. This is C. So the definition of C is omega plus P. And so omega is also C minus P. Right. C is omega tetrameter lift of omega plus P. And then let's just go here, from here to here. We claim this is C to the power P and then U prime, and so mod p-adic. But notice C to the power P, this is C to the power P, P factorial, and then P minus 1 factorial. Wait. Yeah, sure, p factorial. And so this is p factorial gamma p of c. Of course, this is a p times increase. Actually, this should not be difficult because so this is congruent to epsilon minus 1. This is also congruent to epsilon minus 1 modulo p. Right, so this should be congruent. Good. And so we are done.